Hi, if you don't know me, my name is Ryan, and today I'd like to go through the solution to this problem with you guys. The first link in the description below will allow you to interactively solve this problem for free, as well as every other problem on my FE exam playlist that I've solved. I highly recommend you go ahead and solve those problems, since that'll be the only way the concepts are refreshed in your mind for you. That's the only way you'll be ready on test day. I hope you want to solve the problem. Let's get into the solution now. It says a projectile traveling at 150 meters per second is shot into a stationary crate and remains embedded after impact. If the projectile mass is 75 grams and the mass of the crate is 3 kilograms, what is the maximum height change of the crate? So this is a dynamics problem. It's one of my favorite topics to go through. So I'm excited to be doing this problem. Now if we label this first mass 1, and the crate mass 2, we're given that the mass of the first object is 75 grams, and we also know that the mass of the second object is 3 kilograms, and the approach speed of the first mass is 150 meters per second. Okay, so the first thing I think about when I have two objects impacting each other is called the impulse momentum principle. Now, the impulse momentum principle, it says that the integral of f dt is equal to m delta v. The left-hand side is called the impulse, and this is the change in momentum. Now, what's special about the impulse momentum principle is that when we look at the combined system, what we have is zero impulse, and we can say that we have conservation of momentum, meaning that the momentum before the impact is equal to the momentum after the impact. Now, the reason that's true, the reason why we can't just look at, let's say, the ball, is that the ball has no impulse on it until it collides with the crate. And at that point, it would have an impulsive force, a force that's changing in time when it's impacting. Same thing for the crate by itself. If we look at the crate, there's no impulse until collision. And at that point, there's a force that's changing in magnitude as we go into and out of contact. So we can't look at these systems alone. We have to look at the combined ball crate system. Just before impact, there's no impulse. And at impact, the impulsive force is a self-canceling internal force, which cancels out, which allows us to use the conservation of momentum, where we say that the change in momentum is equal to zero, or that the momentum of this ball crate system, the total momentum of the system before, which is the mass of the ball times the speed of the ball before impact, plus the mass of the crate times the speed of the crate before impact, is equal to the momentum of the system after impact. What's the momentum of the system after impact? It says that the projectile remains embedded after impact. That means that both the projectile and the crate will be traveling with the same speed, and that their masses will be combined. So that means that the total mass is going to be moving at one speed, and I'm going to call that speed v. Now note that right before impact, the speed of the second object, the speed of the crate, is zero. It's only after the impact occurs that the crate is going to have some speed. So what we know is that the speed after impact is going to be equal to the mass 1 times the speed of that first object, or the speed of the ball, divided by the total mass. So this is going to be important for us. What we're really looking for is this change in height. Now, what we know is that after impact, we have the crates and the ball, which are embedded into each other, and they're moving on this string. And it's basically a pendulum, right? If we draw the free body diagram of the crates, what we see is that the crate and ball, right? The total mass is m1 plus m2 times g. That's the weight, which points downward. And then we have a upward pointing tensile force. If we kind of draw the motion path here, note that the tension force is always perpendicular to the motion path. What that means is that that force will not do any work. If you ever see a pendulum, most likely what you're going to be have to using is work energy, which is super useful. What the work energy principle says is that the work done by both conservative and non-conservative forces is equal to the change in the kinetic energy of the entire system. Now, that work term could be broken into conservative and non-conservative forces. If it's just the work of non-conservative forces, what that means is that the change in potential plus the change in kinetic energy, or this right hand side, is called the total mechanical energy. That's equal to the work done by non-conservative forces, where non-conservative forces are forces like tension, and conservative forces are forces like the forces due to gravity, or the forces due to a spring, or the forces due to magnetic interactions. Okay, so what that means, since we know that the tension does not do any work, and the only other force inside of the system is the weight, which is conservative, conservation of mechanical energy is applicable. What that means is, let's call the initial time A, and the final time, the time where we reach our final height, B. It means that the kinetic energy at A plus the potential energy at A must be equal to the kinetic energy at B, that position B, plus the potential energy at position B, where that position B is its max height position. Now, all we have to do here is note down a few of these terms. If we pick our datum to be this lowest point, that position A, that means that we have zero potential relative to our datum. We can get rid of that. And at the maximum height, the crate would come to a standstill because it's reached a maximum. If the crate comes to a standstill, that means that the kinetic energy at that position B will be equal to zero. So the final thing that we note is that the kinetic energy at A, that lowest position, must be equal to the potential energy at B if we're looking for the maximum height. If we fill in some of these terms, we know that the total mass of the system is m1 plus m2, 1/2 m times the speed at that point squared, where this v is what we found after impact. That's this over here. That must be equal to the potential energy at B. The potential energy at B is mgh, where m is the sum of the two masses, gh. And you can see that the masses cancel on both sides. What we're left is this final relationship where if we solve for h, which is this delta h here that we're really looking for, is essentially equal to v squared over 2g. And we know what v was from before, right? V is just this term over here. If we go ahead and plug that in, what we have is m1 divided by the total mass of the system multiplied by v1, this entire term squared. If we take this and divide it by 2 times g, then we'll have our solution. We know that m1 was equal to 75 grams, or 0.075 kilograms, and m2 was just equal to 3 kilograms. If we sum those two things up, plug them in here, and plug the speed in here as 150 meters per second, we can go ahead and get our solution. So let me do that. What we get is that the height is equal to 0.68 meters, or 68 centimeters, which is the final answer. Let's go ahead and see if we got that correct. If you're finding this video helpful and want to see more content like this, please like and subscribe. So we're going to go right here, click on this answer, and yeah, we got it correct. Now you can see if we view the solution here, I have some references here to the principle of working energy and impulse momentum. Let's go ahead and check those out. In dynamics, most of these things are from first principles, so it's a lot faster rather than searching the entire reference manual to just think about it based off of the only 3 principles we learn in dynamics, right? Impulse momentum, work energy, and then Newton's second law. So those are your only 3 options. And usually with some simplifications, you can get to the solution. All right, page 108 here, that is this principle right here. where it says that the impulse is equal to the change in the momentum of the system. Here we see the conservation of momentum. If we have impact, this is also a useful relation. This is essentially what we used just now, right? This is conservation of momentum. Okay, so that's where we got the conservation of momentum. Let's look at the work energy as well. On page 106, we see that this is how work energy looks, where we have the potential energy at point 1 plus the kinetic energy at point 1, which is just the mechanical energy. That's equal to the mechanical energy at point 2 if there's no work done by non-conservative forces, which was like the tension. So let's quickly go ahead and go over this solution. The first thing we saw that looking at the combined system, what we have is that for the combined system, there's no impulse. So that means that the change in momentum is going to be equal to 0. That means that the momentum before is equal to the momentum after. If the momentum before is equal to the momentum after, we can find this relationship for the speed, noting that the ball is embedded into the crate after impact. We have something for the speed. Knowing the speed that that combined crate and ball is going to move at, we know that we have energy conservation because the tension doesn't do any work. And the tension being a non-conservative force, which is not doing work, and the only other force being the weight, means that we can use conservation of mechanical energy. Using conservation of mechanical energy, we're able to solve for that final height, the maximum height that that combined system can reach when we convert all of that kinetic energy at that point A that we were calling before to potential energy at that point B we were calling. And we see that the final answer is 68 centimeters. If you find content like this interesting and it's helping you prepare for your FE exam, please consider leaving a like and subscribing for more content like this. Thanks for watching. I'll see you in the next video. Goodbye.